Hello everyone, today we are going to look at the second type of functions introduced in this chapter, which is called logarithmic function. So log function in short is a type of function that takes the term, a form of y equal to a log b, okay, so a log x, and then there's a base called base b. Now to understand what it really is, usually I know there's a lot of things. I mean, there's an A, there's a B in there. I mean, what on earth is going on, right? So let me explain. So what does a log function do? Now, a log function with a base. So for example, let's look at this in here. So for example, when you put log 10 in a calculator, so let's say we call up our trusty calculator, and there is a log button right here. Let's see if I can point it out with my mouse key right here. So if you say log and then you put 10 in there, what it will return is 1. Okay, so log 10 equal to 1. So we're trying to figure out what does log actually do. Let's start by doing that, right? So log 10 is 1. Okay, so what is log 100 then? So you try log 100. So let's try log 100. So log 100. So instead of 10, 100, it says 2. Okay, so log 10. Now, what is 10 can also be written as 10 to the power of 1, right? So when you think about it, 10 is also 10 to the power of 1. And then, so when you put that in your calculator, it returns the number 1. So what about 100? Well, 100 can be written as 10 to the power of 2, right? So 10 times 10 is 100. And so when you put it in your calculator, so log 100 returns the number 2. Now let's try one more. What about log 1000? So wait, what is 1000 in terms of a base 10 exponent? It's 10 to the power of 3, right? Wait. I think you might be seeing a pattern, starting to see a pattern. So if I do log 100, so what does log actually do then? Oh, I do get a 3. Okay, so it looks like what log does is counting the power on the 10. So if you express your numbers in terms of 10 to the power of something, so for example, 100 is 10 to the power of 2. 1000 is 10 to the power of 3. So when you say log 1000, it's asking the calculator 10 to the power of what is 1000, and then it's giving you the result of 3. So what if you try some weird number? So for example, what is this question actually asking? So let's say I do a log of, let's say 50. Right? What is log 50? So let me clean that up. Log 50. What is log 50 actually asking? Okay, so now when you're trying to do log 50, what you're actually asking the calculator to do is you're saying that, okay, 10 to the power of what, okay, equals to 50. That's what you're asking the calculator to actually do. 10 to the power of what equal to 50. Now, and the answer to that question turns out to be 1.69. Okay, so we're going to round it maybe 1.699. Okay, let's round it to 1.699. Now, and then we can test it out. Is 10 to the power of 1.699 50? So 10 to the power of 1.699. Okay, is that 50? Yeah. Oh, okay. So when you say log of a number, it turns that number into 10 to the power of something, and then it basically gives you the result of 10 to the power of what equal to that value, right? Okay, so now there is, however, a base. Okay, so if you look at this equation, there's this little b in there. So the x is our 10, 100, and 1000. So this is like what we plug in, 10, 1000, 100, or the 50 that we plug in. But what about that little base? Okay, so that little base, that b over there, is this value, is the 10. So you're asking the calculator 10 to the power of what equals to whatever number you put in. And that 10 is called the base. Okay, it's called the base. So a lot of time, if you just type the word log, there is automatically assumed that this base is 10. Okay, so I mean, technically speaking, it should be log base 10, and then you have like a thousand, and the answer is 2. But the calculator doesn't have a button for you to put the base on, so it just have this log button, and it replaces the base with 10. Okay, so it's automatically assuming that you mean base 10. Now in this case, we will not deal with anything that's not base 10, so don't worry. So it's going to be base 10. So that b, which is usually not written in there, is base 10. That means you're asking 10 to the power of what equals to that. There are different situations though. I mean, you could ask, for example, a log that has a base 2, and then what you're asking is 2 to the power of what equals to the number that you're trying to do. Okay, so now let's try some of the numbers in here. So let's try log base 10 graph. So we try a log -1, and you put it in your calculator, log of -1. So let's see, what point do we get? We get, we get error, undefined, error. Okay, so this one we actually get undefined. So when I try to do log of -1, I get an answer that is undefined. That means there's no number. It kind of makes sense, because again, you're asking what? 10 to the power of what is -1? You know this question is impossible, right? 10 to the power of anything positive is a big number, so not -1, right? 10 to the power of 0 gives you 1. 10 to the power of negative number, what if you have 10 to the power of -10? Oh, that's just become 1 over 10 to the power of 10, which is still positive, right? You can never get negative value from doing a power. So therefore, -1 is impossible to get. Negative anything is impossible to get. Now, how about 0? What is log of 0? So this, you can use the same logic. 10 to the power of what equals to 0? For those of you who know your, I think it's actually grade 9 or grade 10 when you learn about these exponents, math, if you still remember from your grade 9. Actually, it must be from grade 9 because I'm teaching that right now. I have grade 9 class. 10 to the power of what equals to 0? Nothing. You can't make 0. You can't make negative. You can't even make 0. 10 to the power positive, negative, or 0. 10 to the power 0 gives you 1, for example. You can't make 0 ever. So this is still undefined. Okay, so the graph doesn't exist over there. Okay, can you do a log 1? Log 1. Log 1. Yep, 10 to the power what equals 0? 0. So this one is actually from this rule. 10 to the power of 0 is 1. So log 1 is actually equal to 0. So we have our first point that we can plot. Okay, so when x equal to 1, y equal to 0 for a log graph, which will look something. So 1, 0, right? So 1, 0 is this point. So let's say we put right here. Let's say this is 1. So this point is our first data point, 1, 0. Okay, now, and then it goes. So now we'll use a calculator. So for example, I do a log 2. So log 2, and I get 0.3. Okay, so I'll just do those. So I'll just do those. I'll do a log 2. So log base 10 of a 2 is 0.301. Log base 10 of 3 is 0.477, and so on. So I'll just write down the last two, 602 and 0.699. Now you can see that it's actually not growing very fast, right? So when x is 2, log 2, which is the function, gives you 0.3 and then 0.4 and then 0.6 and 0.9. So it's not going very fast. Okay, so if you plot these data points, something funny happened. So you actually have a function where log 1 equals 0 and then it's not growing very fast. It's actually increasing very, very slowly. So something like this. Okay, so this is the function of y is equal to log x. Now remember, this is log x, but it actually should have a base 10 in there. But people don't write base 10, and your calculator doesn't display that base 10, so you have to assume that there's a base 10. Okay? Now, something funny though, which is, so this graph does have a vertical asymptote. It can never be 0 or negative, right? Like no negative value, no 0 value, so it has a vertical asymptote, a line that you will approach but never touch. Okay, you never cross that line. If you look at this function though, however, and let's say you draw a line that is like 45 degree right through the middle. So this 45 degree line is y equal to x, which is a straight line. And then if you plot the graph that you learned earlier, which is the exponential graph next to it, you see that the exponential graph is actually a mirror image of the log graph. The exponential graph, which is, for example, in this case, since our base is 10, let's say y equal to x to the power of 10. These two graphs are called inverse of each other. They're actually a mirror image of each other. Okay, so now let's start by looking at this purple graph, which is our focus of today. And let's list all its features. It only has one point that's touching the x-axis, and it never touches the y-axis, as you can see. So therefore, y-intercept, well, we don't have any, right? So in terms of y-intercept, we don't have any, so none. Okay, so x-intercept, we have one of them, which is right there. That's the x-intercept. So we do have one x-intercept, and it's usually located at 1, 0. That's the location. So yeah, so it's located at 1, 0. Okay, so domain, which is what are the x values that are possible. So we can only have x values that are bigger than 0. It cannot be equal to 0. It cannot be negative. Range. So this function will actually, if you give it enough time, it will eventually go bigger and bigger and bigger and bigger eventually, right? So all the value in y positively will eventually be rich. All the value in y negatively will also be rich. As you get closer and closer to 0, it will get more and more negative. So in terms of range, which is the possible y value, it can be anything you want. Eventually, the function will cover all of the y value, so all real number. So end behavior, which is from which quadrant to which quadrant. So quadrant, remember, counts from 1, 2, 3, 4 like this. So this graph start at 4, ends at 1. So we say it's from 4 to quadrant 1. Okay, quadrant 4 to quadrant 1. Now you might see sometimes questions just say quadrant 4 like this. If you don't remember the Roman numeral, quadrant 1 like that, and it's increasing. Okay, so increasing is this way, decreasing is this way. So our function is like this, so it's increasing, right? Okay. All right. So now let's look at another one. So what if there is a number in front? Now this is still a log 10 base function, but what is the only difference in here is there's suddenly a 2 in front of it. So this extra 2, what does that extra 2 do? We try to put it in a calculator, at least for the first number I will. So for example, 2 log negative 1 is still undefined. Okay, so that doesn't do anything. So this is still undefined. And 0 will still be undefined. So that doesn't do anything. Log 1 will still give you a 0, even though it's multiplied by 2, because 0 times 2. Remember, so you do a log 1, right? So this is basically what's happening. So you do a log 1 times it by 2. So, but log 1 itself is 0. So 0 times 2 is still 0. So you get a 0. So we still have that the x-intercept right here at 1, 0. Okay, so that's still the same. So we have a point over there. There you go. And then we try all the other number. Now I'm not going to bore you with the actual calculation. You can check it with a calculator. So we get 0.602 when x is 2. We get 0.954 when x is 3. And we get 1.204. Wait, these numbers are higher than these numbers. Can you see that? 0.3. Then we have a 0.6. Okay, so let's compare them. Now 0.3, we have a 0.6 in there. And then 0.4, we have a 0.9. Wait, it looks like it's double. Well, of course it is double when you think about it. There's a times 2 in front of the function. It should have been double. Doubling actually makes sense. Oh, so the graph will actually go slightly higher. But other than that, nothing really changed that much. So comparing these graphs, okay, so let's draw the function. So it will cross that point and then it will go higher. It still has the stupid vertical asymptote that you cannot touch. That doesn't change. You still cannot get negative. You still cannot get 0. But then it goes a little bit faster. It grows a little bit faster than the other one. So comparing these two, one is like this, the other one is like what? Grows a little bit faster, right? That's it. So it doesn't actually make that big of a difference in terms of what the graph looks like when you have a multiply by 2 in front of it. So 2 to the power of log x will look like that. Okay, so fill in all its feature is super easy because it doesn't actually change. How many y-intercept? Nothing. How many x-intercept? You have one of them and it's located at 1, 0. What about the range? All real number. So y exists in all real number. What about a domain? X can only be bigger than 0 and nothing else. And behavior, we start from quadrant 4 and we are moving to quadrant 1 and it's increasing. And that's it. So, and behavior, all done. Okay, so I guess now the next thing. Okay, so we're going to skip some of these items in here because I don't want to be doing this, don't waste too much of your time. So let's cross that one out. Let's do -1. So a negative. So this one has a negative in front. So that's the big difference, right? So y equals to -5 log x. Okay, so this is just y. I mean, it's a name. You can call it Tommy. It's the name of the equation. It's called I of x, which is, they name it I, but it's actually just y when you enter it. Okay, so you can try -1. I can tell you the answer already. It's undefined. Log function can never survive any negative value or 0. It doesn't matter what you put in front. Now, we put a -5 in front. It doesn't matter. Okay, the only difference is that -5 in front, right? Doesn't matter. Still cannot take those negative value. And when you put 0 in it, it's still 0. When you put 1 in it, it's still 0. Log 1 is 0. 0 times -5 is still 0. Okay, so now you have a list of number that will actually work, like when you put 2 in there. So log 2 times the -5 is going to be -1.505, and then -2.386. When you have 3, when you have 4, it's -3.010. When you have 5, it's 3.495. Okay, so these numbers are just negative and 5 times bigger than the number from our original equation. So, but it's negative though. So what would the graph look like when there's a negative in front? So it turns out when the graph look like is, well, first of all, it still has this unavoidable 1, 0 x-intercept. The only thing that's different, right, between this one and the previous one is that it's upside down and it grows even faster. Because remember, the first one that we did was growing at was growing really slowly, and the second one that we did grows a little faster. But it won't be really, really fast. It's still like a very slowly increasing function, okay? But it's upside down. Because there's a negative sign in front, so because of this negative sign, the function will flip upside down. Okay, the 5 has nothing to do with it flipping. It's the fact that it's negative in front. Okay, so if positive, it goes this way. If negative, it goes like this way. Okay, so negative flips it upside down. All right, so if we are to answer these questions, we will do it really, really quickly. And so we have a whole bunch of numbers. So number of y-intercept are none. Number of x-intercept, yeah, there's one. At 1, 0. Domain, x is always bigger than 0. Still the same. Range or real number, still the same. And generally speaking, so and behavior. This time we're actually starting at quadrant 1 and we are ending at quadrant 4. Remember, you're reading it from the left to the right. So this is from quadrant 1 to quadrant 4 and it's decreasing. Okay, it's no longer increasing. All right. Now, so all log function of the form y equal to log x or y equal to, we haven't talked about this one yet. This is going to be on the next page. It's a special version of log. This is what happened when log has a base y. Okay, so log with a base y of x. We call that ln of x. So ln of x is a special base of log. So it's no longer log base 10. It's a base y. Y is a number. Y is a number. We'll talk about that on the next page. Y is actually a number called the natural number. It's on your calculator. So let me see. You take me right here. If you want the y value, I'm going to point it out with my mouse key. That one. That one is on top of the plus sign. So you have to get the secondary function and then that. This is y, 2.718. This is called the natural number. Okay, it's called a natural number. It has something to do with golden ratio and specifically has a lot of relation in calculus. So when you have a log with a special number, think of y as pi. Like think of y as pi, which is like a random number that your teacher tells you, but has some mathematical meanings underneath. So it's like 2.718 ... right? So y is a special number in calculus, in nature, basically. So the reason why it's called natural number. It has a special place in nature. Okay, so when you have a function that is y equal to log x or y equal to lateral log, okay, so ln, lateral log, log of nature, that's why I spell ln, it's log of nature, lateral log of x, you always have these characteristic, which is when the number in front is bigger than 0, the function increase. If the number in front is less than 0, then the function decrease. Okay, so when you have a positive number in front, so for example, let's say, think about it, does this one increase or decrease, right? So lateral log of x, increase or decrease? This one decrease. Why? Because there is a negative sign in front, right? That means the a is -1 in this case, right? So this number is -1. So a is -1, less than 0, so the function decrease. So you can tell if the function, what does the decreasing function look like? So it's either this way or that way. So decreasing is the one that looks like that, right? It's the one that looks like that. So lateral log function. Okay, so moving on to the next page. So predict what this function will look like without using your graphing calculator. Now, this is actually quite easy. So look at this number first, which is bigger than 0. So we all know our function is increasing. So it should look something like that. And it's a regular function with the base being nothing, right? There's no base in here. But no base means that the base is 10. Remember that, right? You have to assume that the base is 10 when there is no base. So your function will have the standard x-intercept over there, and it will just look something like this, right? You can just randomly draw it out there. There, that's what the function looks like. So once you can draw the function, it's increasing, and there's no negative in front. Once you can draw this, then you can answer all these questions. So they ask you, what is the x, where's the x-intercept? Where is it 1, 0? Okay, and then say, okay, so any y-intercept? Nope, no y-intercepts. Okay, and end behavior. So end behavior is from quadrant 4 to quadrant 1. Domain x is bigger than 0. Range y is all real number. So super easy. Basically, you're just looking at the number in front of the log function, and then you're memorizing like 2 different shapes. Okay, what about this one? -4 ln x. Okay, so this will have a, well, again, you'll have that. This. Now, it turns out that a lateral log and log graph looks almost exactly the same. The base doesn't change too much of what it looks like. It will still have this, and it will still have the effect of this negative, right? So when a is -4, so when a is -4, your function is decreasing. Now, this is your base. The base in here is y, 2.718. So base e, base 10 looks almost the same. So your function still looks something like this. It's just upside down because of the -4. Okay, other than that, it's exactly the same as the log graph when there's a negative in front of it. So characteristic, we can say x-intercept, there is 1 at 1, 0. Y-intercept, no y-intercept, so no y-intercepts. And behavior, and that is from quadrant 1 to quadrant 4, and it's decreasing. Domain, x must be bigger than 0. Range, y is all real number. So it's starting to look a lot like it's a repeat, right? So, yep, those are the design function. And let's not do these 2 examples. I mean, you could try it if you want to, but all right, if we were in class, I would actually have you do that during class time. Okay, so let's go through these final few numbers examples and do some matching. So let's see which equation match with which graph. Okay, so we just learned exponential function. So therefore, I think we should start by looking at these 2, exponential function and log function. So let's look at the log function first. So 6 log x, and the other one is -2 lateral log of x. Okay, so 6 log x should be the one that's increasing, so it should look like that. The negative version of that would be something that looks like this, and that should be easy to find. There's only one graph that looks like number 3, which is, I think, is this one right here. See? So this one is positive, right? And we can tell that it's a log function because it has this vertical asymptote and the fact that it goes through 1, 0. So it must be a positive log graph. And the only option that we have for that is y equal to 6 log x. Okay, so this is the only option that we have. So number 1 match, done. So this one is done. So we did that. Okay, what about the natural log? Okay, so the one that looks something like this. Oh, this one right here. Option A. Now, does it go through 1, 0? It has to go through 1, 0. Yeah, it does. It does go through 1, 0. So that's one good thing that we have running for us already. And does it have a vertical asymptote? Yep, it does. Okay, so 2 good things working for us. So it's a negative log function. Okay. So, negative log function, the only one that we have is that natural log one. So it must be that one. So -2 lateral log of x. That's an L, not a I, but sometimes I can squeeze in there. Okay, so that one is done. All right, exponential function. The first one is 5. Okay, so this is the increasing one, the one that's going really quickly. So with A, that should be the increasing one. And B is, so this is the one when the base is negative. So remember, when the base is negative, your function is actually decreasing. So it goes this way instead, right? So the base is less than 0, your function is actually decreasing. Okay, so I think I know which one. This one is the one that's increasing. As you can see, the function increases from left to right. So your y-intercept, also another thing you can tell is your y-intercept is at around 5, which is that number right here. This is your y-intercept. So if you remember from the first day when we did these notes, so that's your y-intercept, that number right here, that 5. So we have a 5 y-intercept and the function is increasing. Okay, and it's an exponential function. Okay, so the only option we have is this one. So then the last one must be this one, which is decreasing, and it has a y-intercept of 2. We can actually double check. See that? 2 right there. So that's your y-intercept, which is at a 2, and it's a decreasing function. So this matches everything. So y-intercept is at 2, and it's a decreasing exponential function. So everything match. So this must be the 2 times 0.1 to the power of x function. Okay. All right. So now that's everything for this week. I will post the questions and everything on the blog post. All right. Okay. Goodbye, everyone.